In this presentation, we're going to investigate if pure liquid or gaseous hydrogen is a viable solution as an aircraft fuel. This video clip contains the following subjects. First, we are going to look at the contribution of aviation to CO2 emissions. Thereafter, we're going to look at the various statements that are made by various hydrogen companies in the media and which are clearly only part of the story. The first one is hydrogen is the most abundant element in the universe. Statement 2 is hydrogen packs around 3 times more energy than jet fuel per unit of weight, so it's the ideal fuel for aircraft. Statement 3 is a hydrogen electric or fuel cell approach is best at converting that chemical energy to propulsion in the most efficient way. Thereafter, we are going to investigate how many wind turbines would be required to power only the European flights with hydrogen. And finally, we are looking at some other considerations on the use of hydrogen in aircraft. First, let's have a look at the CO2 emissions of aviation worldwide. Aviation accounts for around 2% of global CO2 emissions. When we look at Europe, the total greenhouse emissions are 3.8 gigaton of CO2 equivalent. Aviation is around 4% of those total emissions. Let's look at all the statements that are made around hydrogen from its supporters. The one which always pops up first is hydrogen is the most abundant element in the universe or on Earth. While this is actually true, it doesn't exist in its pure form on Earth. The contents of pure hydrogen in the atmosphere is only 0.00005%. All hydrogen on Earth is locked up in molecules, like water, methane, or other hydrocarbons. This means we have to extract them from these molecules, which cost vast amount of energy, which we'll see later. So hydrogen is not an energy source, but only an energy carrier. Even jet fuel has 26 hydrogen atoms locked up in its molecule, which split in water and CO2 when burned. So how do we extract pure hydrogen from these molecules? The first method is the steam methane reforming process. Currently, more than 99.9% of the world's annual 19 million tons of hydrogen is produced in this way. It uses steam of 1100 degrees, which is combined with methane to make hydrogen. 10 kilowatt-hour of methane produces 7 kilowatt-hours of hydrogen. But it also produces a minimum of 9 kilograms of CO2 for every kilogram of hydrogen produced, and is therefore not green. The CO2 is either released into the atmosphere, then it's labeled grey hydrogen, or is captured and buried in, for instance, empty gas fields, and then it's blue hydrogen. Be aware that carbon capture and storage itself is a very energy-intensive process and not at all proven to be effective. Second is electrolysis. This is the process of splitting water in hydrogen and oxygen. It costs enormous amounts of energy, between 50 and 65 kilowatt-hour of energy for 1 kilogram of hydrogen. That's on average 75 cycles of your Class A++ washing machine, but it produces no CO2 and is therefore labeled green hydrogen. But it is only green if the energy of this process comes from a renewable energy source, like wind turbines or solar panels. So to produce green hydrogen will cost enormous amounts of energy. Currently, Only 0.04% of hydrogen is produced in this way. The second statement, which appears in almost all posts about hydrogen aircraft, is hydrogen has 3 times more energy per weight as jet fuel and is therefore the ideal fuel for aircraft. This sounds attractive as it would make aircraft substantially lighter. Hydrogen has an energy density of 33.3 kWh per kilogram, and jet fuel has a density of 11.9 kWh per kilogram, which is indeed around 3 times more. So at first sight this looks attractive because you would need 3 times less weight for the same amount of energy. What they are actually suggesting, and what most people think after reading this statement, is if you take the same amount of weight of hydrogen and jet fuel, hydrogen will have substantially more energy. But they're forgetting an important part of the puzzle here, and that is that hydrogen has an energy volume problem instead of an energy weight problem. So actually this is not a correct presentation. At standard atmospheric sea level conditions, the energy volume relation of hydrogen is only 0.0029 kWh or 2.9 watts-hour per liter, while jet fuel packs 9.52 kWh of energy per liter. The reason for this is that jet fuel is a liquid at atmospheric conditions and hydrogen is a gas at the same conditions. Hydrogen is actually the lightest gas in the world. This means hydrogen packs 32 times less energy per liter as jet fuel. To give you an idea, for the energy of 1 liter of hydrogen, you can power one 3-watt LED light bulb for an hour. While for 1 liter of jet fuel, you can power all the electricity and heating in your house for a whole day. If we go back to our weight scale, it will look like this. If we want hydrogen to produce the same energy as 1 liter of jet fuel, we need 3,200 times more hydrogen in volume at the same pressure. This is actually not to scale as it won't even fit on the page. The hydrogen is still lighter, but we need an enormous amount of volume. So how long can we fly if we would fill up the aircraft tanks with hydrogen at standard atmospheric conditions? At a weight of 200 tons, the fuel consumption of a Boeing 787-9 on a cruise altitude of 35,000 feet with Gen X engines is 1.9 liters of jet fuel per second. 1 liter of jet fuel delivers 9.52 kilowatt-hours of energy. So this is 1.9 times 9.52 is 17.9 kilowatt-hours of energy per second. If we would fill up a Boeing 787-9 tank with hydrogen at standard atmospheric pressure, it would contain 126,370 liters of gaseous hydrogen, which equals 375 kilowatt-hours of energy. This gives us about 21 seconds of flying time, which is totally useless. This means we have to drastically increase the density of the hydrogen. There are 2 ways to do this. Enormously compress the hydrogen or enormously lower the temperature of the hydrogen to turn it into a liquid. Hydrogen is usually compressed to 700 bar or 10,000 psi. But even at this enormous pressure, its energy density per volume is still 4.6 times lower than jet fuel. If we go back to our weight scale, it will look like this. For the same amount of energy, the hydrogen is still lighter, but we need 4.6 times more hydrogen in volume at 700 bar pressure. So this is the actual correct presentation. Another way is to liquefy the hydrogen. But this makes the density per volume only 15% better in comparison to compressed hydrogen. But this presents an enormous challenge, because hydrogen becomes a liquid only at minus 253 degrees centigrade. That's only 20 degrees above absolute zero. So we have to put in an enormous amount of energy to liquefy it. If we go back to our weight scale, it will look like this for liquid hydrogen. If we want both energies to level, we need 4 times more liquid hydrogen in volume as jet fuel. Because we need 4 to 4.6 times more liters of hydrogen as jet fuel for the same amount of energy, and we need heavy and large tanks which can withstand this enormous pressure or extreme low temperatures, it is obvious they won't fit into the wings. This means they have to be positioned in the fuselage, which reduces the payload significantly, or we have to fit large external tanks, which will increase the drag of the aircraft. Payload is, by the way, all the weight of the passengers and cargo which pays for the trip. Another disadvantage of storing hydrogen in the fuselage is that your maximum takeoff weight of the aircraft will significantly reduce to the maximum zero fuel weight. If you want more information on this subject, see my separate knowledge clip on this. Here's another picture of possible hydrogen tank locations, and you can clearly see that for conventional aircraft designs the payload will reduce. What we saw from the previous slides is that conventional aircraft designs are not really suitable as hydrogen planes. If you want hydrogen planes with enough storage capacity for hydrogen, passengers and cargo, they will look like this. These are the so-called blended wing bodies or flying wings. The third statement, which is usually presented, is a hydrogen electric or fuel cell approach is best at converting that chemical energy to propulsion in the most efficient way. Well, if you're looking at efficiency of converting chemical energy into propulsion, the clear winner is battery propulsion at 73% and not hydrogen. Although hydrogen is better than a jet engine, it's only marginal better as a turbopropeller aircraft. But this picture changes dramatically if you take the production of hydrogen into consideration. Here are the efficiencies from source to propulsion. For hydrogen we have to perform the following steps. First, make direct current from alternating current. Then we have to split the water into hydrogen and oxygen using electrolysis. Then we have to compress or liquefy the hydrogen. Thereafter we have to transport it to the airfield and fill the aircraft with hydrogen, which is then finally converted in the fuel cell back to electricity. What we now see is that hydrogen is actually the worst fuel regarding efficiency. Even standard jet fuel is better, but of course this emits lots of CO2. If we would burn the hydrogen in a gas turbine engine, the efficiency drops to around 17%. Battery electric is in this case still the winner. So after we have debunked all these myths, the question arises, how much wind turbines would be required to replace the current European flights with hydrogen. I'll be doing this calculation with the assumption that all flights will be replaced by fuel cell aircraft with propellers. If we look to 2019, aviation burned 95 billion gallons of jet fuel, or 360 billion liters. Roughly 25% of this fuel was for European flights. That means we burned 97 billion liters of jet fuel for all the European flights. If we multiply the amount of fuel with the energy density of the jet fuel per liter, we get an energy demand of 923 billion kilowatt-hour. A fuel cell with propellers is more efficient than a jet engine, so the final amount of energy we need is 692.5 billion kilowatt-hour. However, we lose almost half the generated energy in the production process, so we end up with 1.3 trillion kilowatt-hour of energy generation. If we look at a large modern 8400 kilowatt wind turbine of 140 meters high with a rotor diameter of 136 meters, it will produce on average around 15 million kilowatt hours per year. Remember that this is quite a large wind turbine. It has more than twice the wingspan of a jumbo jet. It can power 6,000 homes with electricity the whole year round. So we divide the 1.3 trillion kilowatt hour through 15 million kilowatt hour, which gives us 89,480 wind turbines, which is a huge number. This is actually a square area of 299 by 299 wind turbines. But that's not all. Wind turbines must be spaced apart to not interfere with each other. A rule of thumb is that wind turbines are spaced apart 7 times their rotor diameter. The rotor diameter of our 8400 kilowatt wind turbine was 136 meters. So that means they must be spaced apart a little less than 1 kilometer. So in the end, we require a surface area of little more than 81,000 square kilometers. The area of the Netherlands is around 41,500 square kilometers. So the wind turbine area will almost be twice the size of the Netherlands. Further challenges on the use of hydrogen are: first, there are serious safety concerns. Only 40 grams of hydrogen has the explosive force of 1 kilogram of TNT, and it takes 15 times less energy to ignite. In a conventional aircraft design, the hydrogen tanks are situated right after the passenger compartment. It is very questionable if authorities are going to allow this configuration. Secondly, refueling is going to be difficult. Due to the extreme high pressure or ultra low temperatures and the fact that you need at least 3 times more hydrogen in volume than jet fuel. It is estimated that the refueling hose will be too heavy to lift by refueling personnel and has to be done semi-automatic. Remember that NASA postponed several space shuttle launches due to hydrogen leaks. Then we have the problem of getting the hydrogen to the airport. As for today, almost all hydrogen in the world is produced right beside where it is consumed. In most countries, the gas grid is not suitable for the transport of hydrogen, because you need a higher flow rate or pressure for the same amount of energy. And we have the problem of hydrogen embrittlement of steel pipes. This means it has either to be transported by truck, upgrade the gas grid, or build an electrolyzer plant right at the airport. As already discussed, if we decide to fly on hydrogen, hydrogen aeroplanes will be significantly different. So is it possible to fly an aircraft on hydrogen? Yes, that is possible, but there are many drawbacks. First, you need enormous amounts of green electricity. Second, there is a possible payload restriction of 15 to 40% depending on the range you fly. Third, we need totally different aircraft designs. Airbus says they have a production model ready by 2035. Fourth, the refueling process is very complicated. Fifth, there is no infrastructure to provide an airport with hydrogen. And finally, it will take a long time to develop, and in the end, when the European flights are flying on hydrogen, it will only save 0.75% of CO2 emissions. Finally, a recommendation. Hydrogen should be used where it makes sense, and that is with applications for which there is no other solution. Currently, hydrogen is mainly used for fertilizer production and conditioning of fossil fuels, which are the red ones on the hydrogen ladder. Let's try to make that green first. That's already a monumental effort. It will require twice the amount of green energy which was produced in the whole world in 2019. This is the end of the video clip. Thanks for watching, and for more information on hydrogen, check our website or follow us on social media.